Welcome to problem solving session for linear algebra. I am Siddhi Balu from IIT Gandhinagar, and today we will discuss problems related to the syllabus from week 12, and that is problems related to normal operators, self-adjoint operators, and spectral theorem. Okay, so we will start with our just a second. So we'll start with the first problem. Let T be a linear operator on a finite dimensional inner product space V. Then we have to check whether the following statements are true or false. So first is that every normal operator is self-adjoint. So this is the question that they want us to check whether every normal operator is self-adjoint or not. So if you don't know the definition, let me just recall the definitions for you. So definition is that let V be a finite dimensional inner product space, and T belongs to LV, that is linear. T is a linear operator from V to V, and we say that T is normal operator if T star is equal to T star T. Okay, so adjoint composed with linear transformation. I mean, they commute. That's what they say, that T star is equal to T star T. And I mean, the order of composition does not affect the resultant linear operator. And for at self-adjoint, we have again V is a finite dimensional inner product space. And again T is in LV. Then we say that T is self-adjoint if T star is T, that is T adjoint is T. Adjoint of a linear transformation T is T itself. So any guesses that every normal operator is self-adjoint? So when we have normal operator, means we have that T star is equal to T star T. But does this imply that T star is equal to T? This is the question. Whether T star T is equal to T when we have T star is equal to T star T. That is, so any guesses, or at least a guess? If you think that this is true, then okay. If not, then that is also okay. But after looking at the statements, any guess? Okay, so the statement is actually not true, because just because we have composition giving us same thing does not imply that the uh, linear transformation itself are equal when we are composing them. Okay, so let us start with this example. I mean, so let T be from R2 to R2, and so I'm fixing this beta 1 comma 0 0 comma minus 1, and this T is such that T linear transformation matrix for T is okay. T beta beta is 0 minus 1 1 0. Okay, when we write this T star and everything, we are actually talking about their linear transformation matrix also follow the same thing. So this is T beta beta, then T star beta to beta will be what? We have proved this. Just a second. T beta beta into T star beta beta, and which is what? It is T beta beta into dagger, right? And so this will be what? 0 minus 1 1 0. And here dagger means what? Conjugate transpose. Just a second. Let me just. So which is 0 minus 1 1 0, right? Just since we are in real matrices, the conjugate does not change anything. We just have to take the transpose. So this will be now identity matrix. If you check, it will be 1 0 0 1. Okay, and if I take this T star T beta to beta, then it will be again T star beta to beta and T beta to beta. Then again, let me just write. Again, it will be conjugate transpose of T beta beta. And since T beta beta is again real, it will be what? 0 minus 1 1 0 and 0 minus 1 1 0. And if you calculate this, this will again be an identity matrix. So in this case, T star T, since they have same linear transformation matrix, they are equal with respect to same basis. So T star beta to beta is equal to T star beta to beta. I hope I wrote the correct. Yeah. So this implies T star with, since we are working on this, we are with, I mean, this representation is with respect to the same basis on both the sides. So, but T star is not equal to T, right? Because what is T beta beta? It is 0 minus 1 1 0, right? And what is T star beta to beta? It is conjugate transpose of this matrix, which is 0 minus 1 1 0. Okay, so this is not true that self-adjoint imply, sorry, normal operator imply they are self-adjoint. Okay, self-adjoint is a bit stronger condition that because self-adjoint will imply it is normal because T is equal to T star. So when we have this thing, T star, it will be what? T into T, because T star is T, which is T square. Okay, and similarly, T star T if I take, then again T star is T and T, which will be T square. Okay, for self-adjoint. Okay, but so self-adjoint is stronger condition. Okay, normal operator is not always self-adjoint. So this is false. Because we know that we can start with any matrix multiplication. For example, T if I take, if I call this matrix A, then T is what? V going to AV. For this linear transformation matrix, T beta beta, sorry, this linear transformation T beta beta will be matrix A again. And when we follow all these things, we get that T star is equal to T star T, but T star is not equal to T. That is, adjoint is not equal to the original linear transformation, but the adjoint and the linear transformation commute. That is, they are normal. Okay. Is there any doubt that what is happening? Like, if somebody is not able to follow anything, please let me know. Or if you don't follow anything, please let me know. Otherwise, I will move to next question.
No, here that T beta beta, how the first that matrix, how it came, because only beta basis is given. What is the transformation?
Okay, the transformation is this. Okay, so if you want, let A is equal to this 0 minus 1 1 0. Okay, and we define T to be V going to AV. Then T beta beta will be this, just matrix multiplication. Here we have standard basis, then it will be this matrix.
Yeah, okay.
Okay. Now is it okay? Then we are working with the linear transformation matrices because we know these things. So yeah. Now is it okay? I mean, this is the linear transformation. A going to V going to A. Yeah. So okay, so this was my so this was the first question, and the other round implication is true because of this thing. Okay, T star is equal to T in this case. So self-adjoint is always normal, but normal need not always imply self-adjoint. So this was the first one. Second is that they are asking whether a real or complex matrix A is normal if and only if LA is normal. Okay.
Now this self-adjoint, whether it is true for complex also, it is not true for complex. Only for real only it is.
What, sir?
No, this T star equal to T for self-adjoint operator, whether it is true for all, for complex, whether it will be true.
For complex, you mean if I have complex linear transformation, then will that be true? Is that your question?
Yes.
Yes,
Suppose
it
my
could be. Okay, so if I take this 0 minus I 0, and what will be dagger of this matrix? It will be conjugate, then transpose of the conjugate becomes this minus I 0, and transfer will be 0. Then in that case, this dagger is equal to same. I mean, so this is complex linear transformation, which is self-adjoint.
no, if it is 0 1 minus I 0.
0 1 minus I 0. This is,
Yeah.
then it not every. I mean,
Okay.
this is not for true for everything, right? It has to be self-adjoint first. Then we can talk about. I mean, I couldn't understand your question actually. What are you asking, by the way? That every what normal linear trans.
No, here suppose I define a. Okay. Okay. Okay.
Mhm.
That was my misunderstanding. Okay. Now clear. No, I was thinking that 0 1 and minus I 0, but that is not a linear.
Yes, I mean
No,
normal
suppose I
need
take
not.
A. Suppose I
Huh.
take A as 0 1
Okay,
I 0.
0 1 I
My
0.
yeah I 0.
Okay, then
I take this as my uh, linear transformation.
yes.
Whether this will hold for the other condition, T star equal to T. That was my doubt.
Okay, so not, we need to check then, because A transpose, A conjugate transpose is equal to, we need to check these conditions, right? We can't just say, for any given matrix, this is definitely not true. Because I just chose this matrix to give a counter example that this is not true. But this, I can very well swap this one with the I. So for complex also, this does not hold, that self-adjoint will, normal implies self-adjoint. But this, in fact, is self-adjoint matrix, which I wrote here. So if you want to give counter example,
No,
and
okay.
yeah. Okay, so this question, they are saying that if A is a real or complex matrix A is normal if and only if LA is normal. So LA we know, but let us say when we say that matrix is normal, so we just gave definition about linear transformation being normal. So the matrix normal is, let A be an matrix and cross n matrix, B and cross n matrix. We say that A is a normal matrix if A into A conjugate transpose is equal to A conjugate transpose into A. Okay, this is matrix multiplication. Okay, and they are asking whether, question is that A is normal, that is the matrix A is normal. Okay, let me write here. Matrix A is normal if and only if LA, we know how this is. So if my A is n cross n matrix, so this will be from Rn to Rn, V going to AV. This linear transformation is normal. Their question. So this is question, whether this if and only if hold. Okay, so any guesses whether this is true or false, or what it will be? Okay, so this is true actually, because we'll start with this linear transformation LA. So LA is normal, right? So LA is normal imply what? That LA star into LA is equal to LA into LA star, right? So this will imply what? Their linear transformation matrices, suppose for any basis LA to beta, and so on. We can choose the basis same for simplicity. Then this will imply that what? I can separate them, right? This we know from the properties of linear transformation matrix, which is equal to LA beta to beta, LA star beta to beta. Okay, and then this will imply what? We know this is like dagger and everything. So if I take beta to be standard matrix, standard linear transformation, this LA becomes A itself. Okay, so if we set beta is equal to standard basis of Rn, then this LA star and LA and everything, or let me write this, LA beta to beta dagger, LA beta to beta is equal to LA beta to beta, and this is again LA beta to beta dagger, right? But since beta is what standard basis, we can simply write this to be A into A into A into A. So this imply what? That A is normal matrix. Okay, and if I want to reverse this, that A is normal matrix, then this will imply what? A the other way around. Okay, then it will imply what? A dagger into A is equal to A into A dagger. But if I, what is my A is equal to? A is LA beta to beta, right? This we know. Since beta is, let me write here, standard basis of Rn. Then this hold. Then again, just matrix, I mean, these are the properties of linear transformation matrices, and we get up to here, and this will imply that LA is normal. So these are like if and only if condition, or let me just write this here, that normal operator. Okay, so LA is normal operator will imply that the corresponding linear transformation matrix, I mean the matrix which is multiplied to get LA is also a normal matrix. Is there any doubt? These are just like properties of linear transformation matrices and how A is associated with LA with respect to standard basis. Is it okay? So we can just work with matrices instead of linear transformation when we want to talk about normality. Okay, because that's what I also did here. I took this A because it's easy to visualize matrices and their conjugate transpose than visualizing linear transformation and their self-adjoint. So that's why when I wrote this T, I first started with the matrix, which was easy to deal with. And then I defined this linear transformation with respect to this basis beta. And I obtained this what I can say counter example and so on. So this is very handy when we work on normal linear transformation on finite dimensional vector spaces. So instead, if you don't want, if you are not, if it is difficult to get counter example for a linear transformation, just try to go with the matrices. If you can find a matrices where this matrix and its self-adjoint satisfy certain property which is giving counter example or example for your whatever statement is, then work with the matrices instead of linear transformation. Yeah. If doubt, please let me know. Otherwise, I will move to next question. Okay, so assume there are no doubts. Please let me know if you have any. So the third question is that if T is self-adjoint, then the eigenvalues of T are real. This is the question. That if T is self-adjoint, so that is we are given that T is equal to T star. They are asking whether eigenvalues of T are real or not. Okay, by the way, T is equal to T star, so T is normal. Oh, sorry, T is self-adjoint. This implies T is equal to T star, and again what I wrote earlier, let me write it again. T is equal to T star T. This implies what? T is normal operator. Okay. So any theorem or proposition which you remember from the lecture? So let me just write this proposition because that will be easier. And it says that let T be a normal linear operator on a finite dimensional inner product space. Then V is an eigenvector of T corresponding to the eigenvalue lambda, then if and only if V is an eigenvector of T corresponding T star corresponding to eigenvalue lambda bar. Okay, so we are given that T is normal operators and they are saying that lambda is, if lambda is an eigenvalue corresponding to eigenvector V, then V is again eigenvector of T star, that is adjoint of T corresponding to eigenvalue lambda conjugate or lambda bar. Okay, so in our case, T is not normal. So if lambda is an eigenvalue of T corresponding to eigenvector V, then we have that since T is normal, or let me just shift this here. In our case, since T is normal, then lambda is an eigenvalue of T corresponding to eigenvector V, imply what? Lambda is an eigenvalue of T star. But T star is what in our case? T star is T, right? So T star T corresponding to V. Okay, so these imply what? Lambda is eigenvalue corresponding to, or we can say V is eigenvector corresponding to eigenvalue lambda and lambda bar. So this will imply what? That lambda is equal to lambda bar, right? Because we know corresponding to distinct eigenvalues, we get distinct eigenvectors. Okay, and if V is eigenvector for two eigenvalues, then those eigenvalues must be equal. Okay, so we know that. So V is eigenvalue corresponding to lambda and lambda bar. Okay, and in our case, T star is equal to T. This condition is important. So this will imply what? That lambda is equal to lambda star. This will imply what? Lambda is real number, right? Any doubts here? So we started with the self-adjoint, but we know self-adjoint linear transformation is also normal. So this will give me, so that's why. So this proposition is applicable only for normal linear operator. Okay. So that's why since T self-adjoint, it is normal anyway. So we can apply this theorem. We said that lambda is linear transformation corresponding, lambda is eigenvalue corresponding to T with eigenvector V. Then lambda bar is eigenvalue of T star corresponding to same eigenvector V. So we are using that since our linear transformation is also normal, and we are getting this. Is it okay? V becomes eigenvector for two eigenvalues, lambda and lambda bar, then they both have to be equal. That's why lambda is real. If you have any doubt, please let me know. I mean, we have also discussed this, that if eigenvector is equal corresponding to two distinct eigenvalues, then those eigenvalues must be equal, kind of thing we did. So if you still have any doubt, please let me know. Otherwise, I will move to next question. So this statement is true. So let me just highlight it that it is true. And now I'm going to next. That the operator T is normal if and only if norm TV is equal to norm V for all V in V. So any cases for this? Thus T is normal if and only if TV is equal to V. Norm of TV is equal to V. Norm of TV is equal to norm of V. Any cases for this?
Hello.
Yes, sir.
Inner product of TV, comma TV.
Okay. TV
Means
comma TV is equal to
is equal to inner product of T
V
star.
comma, yeah, this one, right?
V comma T star.
Okay. Yeah.
T is normal.
Yes.
So V comma
T star V.
T, T, T star V. Yes.
And then we get this.
Yes. T star.
Okay, but we are asked about norm of V and norm of TV. This is, yeah, so this is okay. Norm of TV is equal to norm of T star V. So this is what we get from here. Okay, but what about this condition? Can we talk about norm of V when we have this information? This is completely okay. What this is completely okay. But it gives information about norm of TV and T star V.
Oh, just I try
Hmm.
inside.
Hmm.
Suppose inner product of TV minus V.
Okay. TV minus V. TV minus V. This is what you want to do?
Yes.
Yeah, but this will give us information about norm TV minus norm V, right? And we are asked about norm of TV. And I mean, like this is not equal to this in general. So we can't conclude anything, even if we arrive at some conclusion. And when we have this, we will have this kind of thing. And we don't know how this looks. I mean, what we will do with such terms. I mean, I understood your
Okay.
approach, but I mean, I'm just letting you know that this in general is not, because even if we arrive at some inequality or equality or anything, this is not true in general to talk about this, because this is norm of TV minus V, right? Square, I mean. Yeah, but it's okay.
Okay, ma'am. I'm just trying.
Yeah. I completely agree with, I mean, this is like correct thought process to start with, actually, to start. By the way, this is norm of TV and norm of V. Okay, so we are talking about norm of a vector and norm of when a linear transformation is applied to that vector. Okay, so do you think that that will always remain same? I mean, this TV comma TV is equal to V comma V. Do you think this will always be equal? Because if you, T could be anything, right? So we can, just multiply it by something and the norm will change. For example, if I just start with this, okay, and I can define TV to be anything. I know that we are working with normal, but still T could be anything. Normal is just what T star must be equal to T star T, right? But it doesn't talk about how the norms of vector change. Okay, they just give that the resultant vector when we commute two linear operators is same, but it doesn't give any information about how that vector looks like. I mean, if you start with any self-adjoint, so this is self-adjoint, right? And in this case, when I take this, or then this is self-adjoint, right? T is equal to T star. Then what will be norm of these things? Or I mean, I'm just trying to give you an example where we can think of certain things. Okay, so any guesses? Still any guesses? Or this looks very trivial matrix, then let us, I mean, this is self-adjoint, so yeah, the things will be good. But even if it is not self-adjoint, then in that case, okay, so let me give you this example. So if we take this, because this is kind of not very okay, and T star will be what? Just conjugate transform. Since I told you, I mean, we already proved that linear transformation and working with its linear transformation matrix are one and the same thing. So I'm just writing this. Consider this T to be LA and so on, and this is the A of that LA kind of thing. And 2 minus 3, 3, 2. Okay. And so T star will be what? It will be 2, 2 minus 3, 3, 2 into this matrix, right? 3, 2. And if you multiply this, you will get 2 plus 9, 4 plus 9, 13. This will be 2, 3 minus 2, 3 will be 0. Again here 2, 3 minus 2, 3, 0. And again it is 9 plus 4, 13. And similarly here, T star T is this 2 minus 3, 3, 2. And 2 minus 3, 3, 2. Then this will imply what? I mean, I hope this is okay, right? I mean, I don't need to write this. I mean, A is equal to, or let me just write this. 2, 3 minus 3, 2. And T is equal to LA from Rn to Rn. We going to, or R2 to be precise, AV. I mean, and this is like T beta beta is just representing T and so on, just notation. So yeah, and this will again be 0, 0, 13. You can calculate this, and this will imply what? T star is equal to T star T. Okay, but now if I try to find, so let V is equal to 1, 0, then what is norm of TV square? It will be inner product of TV comma TV, but TV is what? First, let me just write 2 minus 3 or 2, 3 minus 3, 2. V is 1, 0, comma the same thing. It is what? First row, right? First column. 2, or I can write that first column as this. And it will be 4 plus 9, which is 25. Oh, sorry. 4 is 13. Therefore, norm of TV is equal to square root 13. Right, but what is norm of V? It is norm of V square is 1 comma 0 comma 1 comma 0, which is just 1. So therefore norm of V is square root of 1, which is 1. Okay, is it okay? I mean, the norm of TV and V are quite different. So therefore norm of TV is not equal to norm of V. So the first implication, so therefore T is normal does not imply that norm of TV is equal to norm of V. Okay, so the first implication does not hold. Is it okay? So this statement is false in short. It looks like it is true, but this is not true in general. For normal linear transformation, is it okay? Okay, please, if you have any doubt, please unmute and ask. Otherwise, I will move to next question. Okay, so let me start.
This we can.
Yes,
Now
sir.
this question we can do with eigenvalues. We can prove that it is false. Right? TV I can take it as lambda V.
Yes, definitely. Yes, sir. Yes,
Okay.
we can definitely do that. Yes, I mean, if T has some not equal to an eigenvalue, then this will be some multiple time some multiple times V, but here it will be just V. Yeah, definitely. Yes, we can do with that also. For example, in here also, for example, 0 and 2 are for this, if I work, 0 and 2 are eigenvalues, and eigenvectors are precisely this 1, 0, and here it is 0, 1. I can take. These are eigenvectors. And yes, I mean, norm of this again will be some 4, or the root will again give me 2, and here it is. I mean, yes, definitely. You can work with eigenvalues as well, because that will give me, because yeah, if mod lambda is not 1, then norm of TV is equal to norm of lambda V, and since it is then mod lambda into norm V, and yeah, I mean, this will not be equal to V since norm of V, since no. But again, then you have to choose linear transformation smartly, that lambda is not equal to 1 or mod lambda is not equal to 1, and so on. Yeah. Is it okay, sir?
Yeah, okay.
Yeah. But yes, definitely we can work with eigenvalues and eigenvectors. Yes. And now here, this next question, that let T be a linear operator again on a finite dimensional inner product space V, and let lambda is an eigenvalue of T with eigenvector V, then we have to check the following statement again. Sorry, sir? Yeah, I mean, is there any problem that eigenvector with respect to, or with respect to eigenvector V? Okay, then you have to check the following statements. I mean, statements are coming, okay? And this is the given setup for the question. Okay, so this is the setup, that T is a linear operator on finite dimensional linear product space, and lambda is given that lambda is an eigenvalue of T with respect to eigenvector V, and we have to check that whether lambda bar is an eigenvalue value of T star or not. T is just any linear operator. It is not normal or it is not self-adjoint or any of that sort. T is just a linear transformation or linear operator on finite dimensional inner product space. That's it. And then they are given that lambda is an eigenvalue of that T. Then can we always say that lambda bar is an eigenvalue of T star? Any guesses? I mean, do you think that this will always hold for any given linear transformation? Okay, so let us start with this, that we can work with this, okay, directly with linear transformation matrices. Then T star beta to beta will be a conjugate transpose. Then since we are talking about eigenvalues, eigenvalues are what? They are root of this polynomial, right? So lambda is root of or an eigenvalue. Lambda is a root of polynomial. Determinant of A minus lambda I, right? So let us start with determinant of A minus lambda I and dagger of this matrix. Okay. And we proved that last time that it is equal to what? It is equal to determinant of. Okay, so we are now switching from eigenvalues of A to eigenvalues of A conjugate transpose. Okay, so it is equal to what? Determinant of A minus lambda I conjugate. This is what we did in last lecture from last, what I can say. I mean, we know this. Let me just write that. We know this. Okay, so and we proved this last time, in fact. And so this, so if I start with determinant of A minus lambda I, then this is what? So if I take conjugate on both sides, conjugate of conjugate is same thing. So determinant of lambda I becomes what? Determinant of A minus lambda I dagger conjugate, right? Conjugate of conjugate will give me the same thing again. So this I'm just switching the places now. Okay. So this will imply what? Determinant of A dagger minus lambda I dagger, right? Dagger splits over addition or subtraction. This will imply what? Determinant of A dagger, that is okay. And now dagger of this entire thing is what? So understand this, that lambda I dagger is what? It is of this form, right? Lambda, 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 and dagger of this. So it will become what? Lambda bar, so on lambda bar, and transpose. Okay, and this will be same thing because it is diagonal matrix and it is n cross n matrix. Also, let me write n cross n, n cross n, n cross n, and these are diagonal entries. So this is what? Lambda bar I, right? Conjugate of lambda into I. Okay, so this will give me what? That determinant of A minus lambda I is equal to, from this and this what we have obtained here is determinant of A conjugate transpose into lambda bar I, right? Whole conjugate. Okay. So when determinant of A minus lambda I is 0, that is if lambda is an eigenvalue of A, then this imply what? Determinant of A minus lambda I is 0. So this will imply what? Determinant of A minus lambda I mean this perp and bar and everything is 0. But since we are comparing it with the 0, I mean it becomes, I mean we can omit the conjugate, or let me just write that as well. Minus lambda bar I conjugate is equal to 0. And if I again take conjugate of this, it becomes 0. Determinant of A minus lambda bar I is equal to 0 bar, but which is again 0. Okay. So this imply what? That lambda bar is an eigenvalue of this thing, right? This is by definition. By definition. Or not by definition, I mean, yeah. By the property of eigenvalues and so on. Is it okay? So we started with eigenvalue of lambda. First, we simplified how the determinant of A minus lambda n and how the determinant of A conjugate transpose minus lambda bar I are related. And then we started our basic implication in calculation, or we see how the things lead to what we need. Okay, so A is eigenvalue of A, lambda is an eigenvalue of A. So this will imply that this determinant is 0. Then this will imply what? This determinant is 0. And by the definition that this determinant is 0 gives us that lambda bar is an eigenvalue of A conjugate transpose. Okay, so that's why this statement is true, that if lambda is an eigenvalue of T, then lambda bar is an eigenvalue of T star. That is, conjugate of lambda is an eigenvalue of adjoint of T. Is it okay? If there are any doubts how this calculation and everything.
Yeah, ma'am, there is a doubt. You are using a word dagger. What do you mean by dagger?
It's
A dagger.
conjugate. So A dagger is just a notation for A bar transpose. Conjugate of A
Transpose
and then
conjugate.
transpose. Yes, conjugate transpose. This notation here is called dagger. So yeah.
I think in most of the books we are using the symbol A theta.
Okay, sir. But in the notes we have used this notation. If you see, and even the lectures, we have followed this notation.
Yeah.
So that's why I'm consistent with the lectures. Yeah. Okay, but we can have. So for example, if you want, you can just write it that A star, because it is corresponding to this linear transformation LA star, right?
Yeah.
That doesn't matter, but yeah. But in the lectures, we have used this symbol dagger. So that's why I'm following the
That
same
means the
from the
transpose
lectures.
conjugate. That's what.
Yes, sir. Conjugate, transpose, conjugate, yes. Both will be same, okay? Conjugate, transpose, conjugate will be the same thing. Yes.
Yeah.
Yeah. Okay. So now, sir, is it okay?
Yeah, ma'am.
Okay. So second one, then V is an eigenvector of T star corresponding to T. So this is the question. So we already given that T is a linear operator. It is any linear operator where lambda is an eigenvalue of T corresponding to eigenvector V. And now they are asking that the same eigenvector will work as, eigenvector of T star corresponding to eigenvalue lambda. Okay, so this we had for normal. If you remember, I just wrote statement, I guess somewhere. Yeah. So if T was normal linear operator, then this is if and only if condition that this always hold. Okay, but T could be now any linear transformation. So in that case, can we always say this, that if V is an eigenvector of lambda, then corresponding to T, V is an eigenvector of T corresponding to lambda, then can we always say that V is eigenvector of T star, that is self-adjoint of T, corresponding to eigenvalue lambda bar. We know that lambda bar is an eigenvalue of T star using this statement. What we prove in part 1, that if lambda is an eigenvalue, then lambda bar is an eigenvalue of T star. But the same eigenvector also follows. That is, let me write, if TV is equal to lambda V, then T star V is equal to lambda bar V, whether this implication is true or not. That is the question. Any guesses for this? If true, then let us start the proof. Or if not, then can someone give me example? Okay, so as since the statement which was proved was for normal operator. If that was true for any linear transformation, then that statement would have been proved for any linear transformation. But that, of course, is not true. Okay, so can someone give me the example of T such that the eigenvector doesn't follow? Again, you can think of matrices, and so that it will be easier to think of. And definitely you can work with linear transformation if you are comfortable with it. Okay, so if not, then let me give an example. So I will work with matrices. Okay, so someone was saying something. If you have any examples, please. Otherwise, oh yeah. Okay, so A is V. So definitely lambda is equal to 1 is an eigenvalue of A. Okay, since this is upper triangular matrix, diagonal entries are eigenvalues and so on. Okay, so lambda is an eigenvalue. And also V is equal to 1, 0 is eigenvector. Okay, it is quite eigenvector corresponding to because see A1 or AP is equal to 1, 0, 1, 1, 1, 0 is equal to again 1, 0, right? Into 1. So therefore we already have this information with us. Okay, so A is there and we can tell A is from R2 to R2 such that we going to AV and we are working with this A and AV and LA. Let me just write this. At any moment, if you think that I'm just doing something which is not understandable, please let me know. Okay, so this I have, then A dagger will work as LA star, matrix for LA star. So A dagger is what? Again, 1, 0, 1, 1, conjugate transpose. But since we are in real, conjugate doesn't change the original matrix and transpose is what? 1, 1, 0, 1. Okay, then now this LA star is just R2 to R2 with V going to now this A dagger V. Okay, and what is then again, since 1 is an eigenvalue, or let me write 1 is an eigenvalue of A, this or LA, this implies that 1 bar, which is again 1, is an eigenvalue of LA star. This is okay from part 1 of this question. Okay, so this, if I try to do that, then if I take AV, so our question is whether the same eigenvector which was giving us AV is equal to lambda V, whether that same eigenvector work for this lambda bar or not. Okay, so V was this for our linear our lambda. So A dagger V is equal to what? 1110 into V is this. And now this is 1, 1. Okay. And this is definitely not equal to 1 into 10, right? So therefore, A lambda V is not equal to lambda bar V. Okay. Or is it okay? So this, therefore, this statement is not true. That the same V does not serve as the eigenvector of lambda bar. Okay, so if V is an eigenvector of lambda for T, then the same eigenvector does not work as an eigenvector for lambda bar of T star. I hope what I said was correct, but yeah. Sorry, sir?
Anji.
Okay. So if this is okay, then I would like to move to next question. If you have any doubt, please let me know that how things are following. Okay. If not, then let's go to third, that if T is a norm, if T is normal, then V is eigenvector of T star corresponding to lambda bar. Okay. And this definitely is true from this proposition which we already gave here. Okay, so let me just copy this. Okay. And this proposition directly gives us this statement. That if T is normal linear operator, then this statement is in fact if and only. Okay, so therefore this statement is true by this proposition. Any doubts here? So V does not serve as an eigenvector corresponding to lambda bar for T star if T is any linear operator. But if T is normal linear operator, then the same V serve as an eigenvector for lambda bar for T. Okay, so these were to highlight those properties of T and T star and how the eigenvectors and eigenvalues are related to each other and so on. Okay, now this one, that we say that T is unitary if T star is equal to T star T is identity. Okay, where I is the identity matrix. Now the question is, if T is a unitary operator, then they are talking about this mod of lambda. Okay. And what is your guess in this case now? T is unitary. Unitary means it is stronger condition than normal, because here T star, apart from T star T being T star being T star T, it has to be equal to identity matrix as well. Okay, so this is something extra than the normal property of a linear transformation. So any guesses in this case? Okay, so if not, then so they are talking about the lambda of unitary operator. Okay, so let us first start with, let lambda be an eigenvalue of unitary operator T. Okay, so this imply what? T star TV is equal to, we have this, okay, and from this we also have this lambda TV is equal to lambda V. Okay, we know this whole. So if I take TV comma TV, or since T star TV is equal to V, these imply what? If I take this inner product, TV comma V is equal to V comma V, right? So this will give me what? TV comma TV is equal to V comma V. And this will be equal to what? Lambda V comma lambda V, right? Because V is an eigenvector. Okay, is equal to V comma V. And using the properties, we take this lambda into lambda bar, V comma V is equal to V comma V. Okay, and note that since V is an eigenvector of T, this implies V is non-zero. This implies this norm of V comma V is non-zero, right? So from here, I can get that lambda bar, I can just cancel them, is equal to 1. Okay, since V comma V is non-zero. So this will imply what? Mod of lambda square is 1. This implies mod of lambda is 1. Is it okay?
Ma'am, one step I didn't get. How you got lambda, lambda conjugate. How did you?
So it is complex. The definition.
The product space of lambda v comma lambda v to lambda conjugate v comma v.
This one from here to here.
From one step back to that step.
From here to here. So this is a property of inner product, right? The coefficients come back. So CV comma W is equal to CV comma W. But if I have V comma CW, then it is C bar V comma W. This is property of inner product. So I'm just following that. So from lambda, from the first coordinate or the first entry, I'm getting lambda outside, and thus from second, I'm getting lambda bar outside. So that's why from here to here I got this. Is it okay now?
Yeah.
Okay, any doubts? And this is just complex property or the definition and modulus of complex numbers and so on. This thing was important to realize that this, or let lambda be an eigenoperator corresponding to eigenvector v, that is tv is equal to lambda v, and then this follows. T star tv is equal to iv and v and so on. Is it okay now? If you have any doubt, please let me know. Otherwise, we can move to next question. Okay, so let us move to next question now. That let V be a finite dimensional inner product space and T be a linear operator on V. Then we have to again check the following statements are true or false. Okay, so first statement is that if V is a real inner product space, okay? V is a real inner product space and real inner product space. And T is a unitary. T is unitary linear transformation or linear operator. Then T is diagonalizable. This is the question. That V is real inner product space. T is a linear operator. T is a unitary linear operator on T, on V. Then they are asking whether T is diagonalizable or not. T is unitary means what? T star is equal to T star T is identity. So after this, can we conclude that T is diagonalizable? I hope you know what T diagonalizable means, that there exists P and D such that PDP inverse is equal to P beta beta is PDP inverse, where P is invertible and D is diagonal, and D is diagonal with the eigen entries. And but we are not going to do this. There were many properties which we used to conclude that whether linear transformation matrix is diagonalizable or not. I mean, having distinct eigenvalues equal and corresponding eigenvectors and so on. But for now, V is just a real inner product space and T is unitary. Can we conclude that T is diagonalizable? Okay, so this is not true in general. So again, I will be giving an example with matrices. And we know that this matrix is not, that A is not diagonalizable, right? since this is real, okay, so this is real, so this is not diagonalizable. Over real, right? Since it does not have any eigenvalue in R. Okay, because determinant of A minus lambda I will be 1 plus lambda square. You can check this. Or lambda square plus 1. So or minus lambda square plus 1 or anything. But ultimately, no. Yeah, lambda square plus 1. So this does not have, this is not diagonalizable matrix. But if I take T star, that is A into A dagger, then this is just 0 minus 1 1 0 and again 0 1 minus 1 0. Then it is identity matrix. We just calculated this earlier as well. Again T star T is A dagger A, which is 0 minus 1 0 1 1 0, and this is 0 minus 1 1 0, and this is again identity matrix. Okay, so T star is equal to T star T is identity, in fact. So this is identity. This is identity, but T is not diagonalizable. Is it okay? We know that this matrix is not diagonalizable, I hope. Is it okay? So this statement is false, okay? This does not always hold, that if T is unitary linear operator, then T will always be a diagonalizable. That is not true. Is it okay?
Ma'am, can you just once more tell when we say that a matrix is diagonalizable? I mean, what is the condition that we have to?
Okay, so T is diagonalizable if we can write this linear transformation matrix of T as PDP inverse for some invertible matrix P and D is equal to diagonal lambda 1 to lambda n containing the eigen values of T. Okay, so this, and we had conditions that this is always, T will always be diagonalizable if T has n distinct eigenvalues, and if have n distinct eigenvalues, then uh, then we then it will have n distinct eigenvectors, and those eigenvectors when will give us information about this P, and we can have that is diagonalizable. Apart from that, if dimension of E lambda, if first is that it should have n eigenvalues. Okay, for example, this linear transformation does not have eigenvalues in real. Okay, so first of all, our if it does not have eigenvalues in the given field, it is not diagonalizable. Secondly, if it has eigenvalues, if all the eigenvalues are distinct, so if T is from V to V and dimension of V is n, then if T has n eigenvalue, need not be distinct. If all of them are distinct, then it is definitely diagonalizable. If it is not distinct, then dimension of this E lambda, if it is equal to multiplicity of lambda for all eigenvalues lambda of T, then T is diagonalizable. This is the condition. This is the main condition of T being diagonalizable. And dimension of E lambda means dimension of eigenspace corresponding to lambda, and multiplicity of lambda means how many times lambda is repeated. For example, if I talk about identity matrix, then eigenvalues lambda is 1, 1. Okay, there are two eigenvalues. 1, 1. They are repeating only one eigenvalue, but with multiplicity 2. And so on. Is it okay, sir? I mean, these are the conditions which are like explained in the lecture, and also we have discussed problems related to the diagonalizable and so on. But this is the main thing which is enough to work. Is it okay?
Is there not one related to characteristic polynomial? If it splits, then
Yes, when I said that, I mean the distinct eigenvalues will serve that. And that split is for a complex thing. I mean, in real, it need not split. For example, this yeah. If it splits, then yes. And yeah, I mean, even if it splits, it need not always be diagonalizable. For example, this matrix, if you work on, this matrix is not diagonalizable, I think. There are two, for example, lambda minus 1, it splits two eigenvalues, lambda minus 1, but right, when you say split, you mean distinct, or you just mean that it has n roots? Okay, but this is not, you can work with it, that this A is not, oh sorry, diagonalizable. Just split does not serve as diagonalizability in R. And even in complex, because the same example can be transferred to complex. And this is still not, because only eigenvalue is 1 and AV is equal to V. If I take, then it will be what? 1, 1, 0, 1 xy is equal to xy, right? Because 1 is the eigenvalue. And it will be what? Xy. And when I multiply this, it will be x plus y. And here it is y. So this will give me what? X is equal to y and y in R. So dimension of E, so E lambda is what? 1, 1, I guess. I hope. Oh, sorry. Y in R, because y is equal to y, and x plus y is equal to x. This implies y is 0 and x in R. So this implies x in R and y is 0. So this implies E lambda is just 1, x 1, 0, where x is in R. Therefore, dimension of E lambda is 1, but multiplicity of 1 is 2, therefore not diagonalizable. So split does not always serve as diagonalizability. I mean, split does not guarantee the diagonalizableness of matrix or linear transformation. Is it okay, sir? I mean, split does not always guarantee the diagonalizability, but yeah, this condition will always be sufficient to conclude whether the given linear transformation or a given matrix is diagonalizable or not. The one which I highlighted, let me highlight it once again. This one. Okay. When we say split, if it is splitting and giving us distinct eigenvalues, then definitely it is diagonalizable. But if the eigenvalues are repeating, then we have to check whether the multiplicity is equal to the dimension of that corresponding eigenspace of or not. Is it okay, sir?
Yeah.
So let us move to. So I hope you understand. I mean, it is clear with this that real that things are a bit tricky. But even if in complex, even if the everything splits and but still we cannot guarantee the diagonalizability. And second one is that if V is complex inner product space and T is unitary, then T is diagonalizable. Now, any guesses? Since now we are switched to complex inner product space. Okay, the complex inner product space, the assurance is that T splits. I mean, the linear characteristic polynomial splits. So it has at least n eigen values and so on. And along with that, we have this condition that TT star is, so complex adds this condition that characteristic polynomial splits and along with this we have this condition that TT star is equal to T star T is equal to identity. These two conditions are important. Then can we say anything about this? Okay, so first note that T is unitary. So this implies T star is equal to T star T is equal to identity. So this also implies that T is normal operator, okay? And we then have this spectral theorem for normal operator. And it states that let V be a finite dimensional complex is important, complex inner product space. And our T is linear operator. And let T be in fact normal linear operator. Then there exists an orthonormal basis of V consisting of eigenvectors of T. Okay. So does this help anywhere to conclude that T is diagonalizable? Okay, so this statement itself is enough to conclude, because then what? Then first the characteristic polynomial is split, then we will have n eigenvalues, and then corresponding to each, since we have orthonormal basis giving us eigenvectors. So there is orthonormal basis consisting eigenvectors. So it will give us. So this was also one of the results which were helping us to talk about the diagonalizability, that if we have a basis consisting eigenvectors of T, then T is diagonalizable. And here, in fact, we have orthonormal basis consisting eigenvectors of T. So therefore, this statement, so let me write here. Therefore, true using above theorem. Any doubts here, like how things are? And one thing, that dimension of E lambda is always less than equal to multiplicity of lambda. This statement is also explained in the lectures. Okay, so since dimension of E lambda will add up to dimension of V, okay, and multiplicities of lambda will add up to n, because if T is from V to V and dimension of V is n, then there are n many eigenvalues, and this is less than equal to n. But now we are given that all the eigenvectors are giving us the basis of eigenvectors. So, sorry, basis of V. So dimension of this V will be n. And so therefore, which is equal to n, and everything falls into the places. Is it okay? If there are doubts, please let me know. I will again explain. Any doubts? It just follows from the properties of diagonalizability and the fact that T is unitary and complex, and the spectral theorem which is there to help us. Still any doubts, please let me know. Otherwise, I will move to next question. Again, T being complex is important. Okay, the spectral theorem is applicable only for complex inner product spaces. It's not true for real inner product spaces. Okay, so now again we are back to V be a real inner product space. Real inner product space. And T satisfies T star is equal to minus T. Then can we conclude that T is diagonalizable? T star is minus of T. Now can we conclude that T is diagonalizable? Okay, so again we will be working with this same example, I think. And here T star is again this matrix, and which is 0, 1, minus 1, 0. This matrix is not, so T star is equal to minus of T, right? this is equal to minus of t. But so therefore t star is equal to minus of t, but t is not diagonalizable. Again, this does not have eigenvalues in real. T minus lambda I. Okay. Any doubts here? The same example serves for this because t star is minus of t in this case, and t is not diagonalizable.
No,
Not.
is it? Ma'am,
Sorry, sir. Yes, sir.
the statement is true for complex networks.
Statement is true for.
Complex network
Yes,
space.
yes. It was the next question on the line, that if it is complex, then whether it's true or not. Yes, it is true in the case of complex. Yes, if instead of real, if I take complex, then this statement is true. Sir, could you please give me the explanation why this is true? Your guess is completely correct. So this statement is true, and
I guess from your example, ma'am, but I don't know
yeah, yes,
proper proof.
yes.
Uh,
I mean, we actually don't even need to prove this. First thing is that since t star is equal to minus t is given, then what is t star? It is t into minus t, right? Which is minus t square. And what is t star t? It is minus t into t, which is again minus t square, right? So therefore, this t is normal. And once we have normal in complex, then again by spectral theorem for normal operator, this will be diagonalizable. So again by spectral theorem for normal operators, we conclude that T is diagonalizable. Okay, eigenvectors forming basis for T is also one of the conditions for T being diagonalizable. Okay, for example, this, just a second, let me show you this example which I wrote. For example, this, I do not need to actually, for this one I'm talking. I mean, this 1001 is forming basis for our linear transformation, our matrix. And these are eigenvectors which are forming basis for R2. And we can conclude that this is anyway a diagonal matrix, but this is one of the conditions, as sir was asking me that what are the conditions to talk about diagonalizability. So this is important condition, but if looking at the matrix, you can, or linear transformation, you can directly conclude that these are the vectors which anyway form, which are eigenvectors and form basis for the given linear transformation. Then also we can conclude that T is diagonalizable. And in here, our V is complex inner product space and T is normal. So by spectral theorem, we can conclude that T is diagonalizable. But yes, sir, your guess was correct and this statement is true for. But normalness does not guarantee T being diagonalizable in case of real inner product space. So that is one thing we can keep in our mind. Any doubts? Or let me just write this, that if eigenvectors form the basis of V, of T forms a basis of V, then T is diagonalizable. Please check this condition, and using spectral theorem and this statement, we can conclude that T is diagonalizable for this fourth question and second question as well. Okay? If okay, then shall we move to next question, or do you still have any doubt? Okay, to arrive at this T being normal is important, because the spectral theorem is true only for normal operators and not for any given linear transformation or linear operator. Is it okay, sir? Or is it okay to everyone? If you have any doubt, please let me know. Otherwise, I will then move to next question. Now, question 4, that suppose T is normal operator on V. Okay. And let V, W in V be such that TV is equal to root 6V and TW is equal to 5W. And they have given if norm of V is 2 and norm of W is 1, then find the value of norm of T, V plus W. Okay, so we have to find the value of T of V plus W. We are given that given is what? TV is root 6V and TW is 5W. And norm of V is 2, norm of W is 1. T is normal, and important thing, T is normal. Any guesses how to proceed?
Norm of T V plus W whole square.
Yes. Is equal to, okay, square, okay. Is T,
Product.
yeah. T, okay, T plus W.
TV plus TW.
Okay, TV plus TW, yeah. Yes, sir. Then this is TV, comma TV. Oh, so I'm not writing brackets. TV, comma TW plus TW, comma TV plus TW, comma TW, right, sir?
Yes,
And yeah, so TV we will substitute with this root 6 and root 5 and so on. So root 6 TV was root 6V, root 6V plus this is, okay, root 6V, comma 5V, 5W plus this is 5W, comma root 6V plus 5V, 5W, 5W, right? And this is what? This is 6, root 6 into root 6. Bar will be, since these are real numbers. Here 5 root 6 V, comma W. Again, I'm ignoring the bar because these are real numbers, or let me just write for the completeness. 5 root 6 bar W, comma V plus 5 into 5 bar W, comma W. And this is what? 6 norm V square plus these things are still there, 5 root 6 V, comma W plus 5 root 6 V, comma W plus this is 25 norm of W square, right? And then if we substitute norm of V was 2, then 6 into 4, or let me write 6 into 2 square, 5 root 6 V comma W, plus 5 root 6 W comma V, W comma V, plus 25 into 1 square. And this becomes now what? 36 plus 25 plus these two terms plus 5 root 6. Can we somehow get rid of these two terms? Any guesses for this? Because we still need, yes.
In place of 36, that means that's 24.
Oh, sorry. Yeah, sorry. This is 24. Thank you, sir.
Okay.
6, 4, yeah. Yeah, sir. So this much is fine. Okay, we calculated it correctly till this. But what about these two terms? We don't know anything about what inner product of V and W is. But from here we can conclude one thing, that V and W are eigenvectors, right? So these two things simple. So any theorem which we
0.
can, yes. So it will be 0. And why? Because of this proposition which we proved in the lecture, that let
They are
T be,
linear.
yes, they're orthonormal to each other. In fact, T must be normal operator. Okay, so T is normal operator on finite dimensional vector space. And then we have that, suppose lambda 1 and lambda 2 are two distinct. Distinct is also important, since here we had root 6 and 5 as our eigenvalues, which are definitely distinct eigenvalues of T, and V1 comma V1 and V2 are corresponding eigenvectors. Then V1 orthogonal to V2. Okay. V1 is orthogonal to. This is the theorem. So since V and W are eigenvectors of normal operator T corresponding to distinct eigenvalues root 6, 5 respectively, V is orthogonal to W. That is, inner product of V, W is 0. And then from here, we can conclude that norm of T of V plus W square is 49 plus 0 plus 0. And this is 49. And this will imply norm of T of V plus W is equal to square root 49, which is 7. Any doubts here? Okay, so this, because of this proposition, these two terms, we could get rid of these two terms.
Now this V and W orthogonal, is it valid only for normal operator?
Yes, the normal operator condition is important. Otherwise, they are linearly independent, but we can't say that they are orthogonal to, or sorry, they are orthogonal. Inner product need not be 0. Is it okay?
Okay.
Okay. So next. Okay. Now this is okay. Yeah. So it is like consider M2R. So now we are in M2R and the vector space of 2 cross 2 okay matrices over R with the inner product A comma B is equal to trace of B transpose A. And our linear operator is T from M2R to M2R such that A is going to A transpose. Okay. So first is we have to check whether the following statements are true or not. Okay. First question is that T is normal operator. Can you conclude this that T is normal operator or not? So T is given, A is going to A transpose. Can we say that T is normal? Any guesses? Okay. So how to start? First is, okay, so what I did was I first tried to find what linear transformation matrix of this linear transformation look like. And once I have that, I can then after that I just have to work with that matrix, because working with the matrix and its conjugate transpose is easier compared to working with the linear transformation and its self-adjoint. Sorry, not its self-adjoint, it's adjoint. Okay, so working with the matrix and its adjoint is way more trickier than working with the matrix and its conjugate transpose. So what I would like to do is I would start with the basis of this matrix. Okay, that it is 1 0 0 1. We know this 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. Okay, this is basis. And if I want to, if I take this is E1, E2, E3, E4, then T of E1 is what? Now again, I want to find the linear transformation matrix of this linear transformation. Then T of E1 is again E1. It is E1 transpose, which is E1. So it is just E1. Okay. Or T of E2 is E2 transpose, which is E3. Okay. And T of E3 is E3 transpose, which is E2. Just see how these matrices are working. And T of E4 is E4 transpose, which is E4 again. So if I want to write this as a linear combination of E1 to E4, this is just 1 E1 plus 0 E2 plus 0 E3 plus 0 E4, which is 0 E1 plus 0 E2 plus 1 E3 plus 0 E4. This is 0 E1 plus 1 E2 plus 0 E3 plus 0 E4, and this is 0. Let me write dots here. Avoid. Okay, E1 plus 0 E2 plus 0 E3 plus 1 E4. Okay, so how this T beta beta look like? It is 1 0 0. Just follow this. 0 0 1 0 0 1 0 0 and 0 0 0 1. Is it okay? So this is linear transformation matrix. Then what is T star beta beta would be? It is just T beta beta dagger, right? And it is again real matrix. I just want to take transpose of this. And what is transpose of this matrix? It is the matrix again itself, right? Okay, so therefore T. So from here, I can just write that T beta beta is equal to T star beta beta, right? So these imply T is self-adjoint. And this imply that T is normal, right? We know T being self-adjoint imply T is normal. So therefore, this is true. Any doubts here? Please let me know how these things are working. Any doubts? Please let me know. And second question was that whether T is normal operator but not self-adjoint. And this becomes now false, right? Because we just saw that false as T is self-adjoint. So working with matrices is way more easier. I find it way more easier than working with linear transformations directly. So that's why I try to obtain the linear transformation matrix of this given linear transformation. Because see, T star T here, the linear, the inner product is this. Okay, then working with this inner product to get T star T, inner product with T, T star, and so on would be a bit trickier. Even if it is easy, because it will be just transpose of a matrix is equal to transpose, and we will arrive at the conclusion. That is not a problem. But still, that won't give you the feel that they are actually normal and so on. So that's why I converted this linear transformation into linear transformation matrix and then worked on this. Because see, now even if someone asks me about the eigenvalues, eigenvectors, and so on for this linear transformation, I can easily obtain that. Okay, so T is a self-adjoint and T is also normal. And if, as next question asks, that find the smallest, let me just, if I call this question A and this B, find the smallest eigen value of T, or smallest and largest eigenvalue of T. Then I can just work with this matrix, determinant of T beta beta minus lambda I. Okay, and what I will get? It is determinant of 1 minus lambda 0 0 0 0 minus lambda 1 0 0 1 minus lambda 0 0 0 0 1 minus lambda. And if you try to solve this, it is 1 minus lambda into minus lambda into minus lambda into 1 minus lambda minus 0 minus 1 into 1 minus lambda, and this will ultimately give me 1 minus lambda cube lambda plus 1. Okay, this will add up to lambda plus 1, and this subtraction and everything will give me this. And therefore lambda possibilities are 1 1 1 and minus 1. Okay, so therefore smallest eigenvalue, smallest lambda is equal to minus 1 and largest lambda is equal to 1. Okay, so for even calculating linear eigenvalues and eigenvector of this linear transformation, working with its linear transformation matrix is easier. Is it okay? Like how we are proceeding and everything? I mean, if you have any doubt, please let me know. Hello.
No, madam, clear.
Okay, so that's how the eigenvalues and eigenvectors work. Please work. I mean, is it okay if I go ahead with next question, or if you want, we can stop as we are past time, or if you want, we can work with one more question. Just it is related to this same question, or I will just write the question. You can work with this. Does there exist an orthonormal basis of M2R consisting of eigenvectors of T? And what is your guess for this? Does there exist an orthonormal basis of M2R consisting of eigenvectors of T? Please understand that this M2R is over R. M2R is over R. So can you... They are asking whether there exists an orthonormal basis of M2R consisting of eigenvectors. Any guesses for this?
Only for complex it is true.
Yes, definitely. If my T was complex inner product space, or if I consider this T as complex inner product space, then definitely inner product space, then definitely true. But our given linear transformation is given that T is over R. Okay, so T and its eigenvalues and everything is over R. So how can you go ahead with this? Okay, so it will take 5 minutes, but I think it's worth doing this. So from here, we already have the information about eigenvalues and eigenvectors of eigenvalues of lambda. Okay, so we just have to work with these two lambdas. So what is my linear transformation? T is from M2R to M2R. It won't take much time, such that A is going to A transpose, right? So for lambda is equal to 1, what is it? So T of V is equal to V. If I start with 1 into V, then let V is equal to ABCD. Then it is ABCD transpose is equal to ABCD, right? Because that is my TV is. Then it is ACBD is equal to ABCD. And this will imply what? A belongs to R, D belongs to R, and C is equal to B belongs to R. So E lambda becomes this 1 0 0 0 0 is equal to span of this thing 0 1 0 0 comma 0 0 0 B is equal to C and so on. Is it okay? Just I'm just writing this. Okay, you can conclude this from here. Okay, so D position correspond to this, B is equal to C correspond to this, and A in R correspond to this. So E lambda is equal to 1 is span of this, and for lambda is equal to -1, TV is equal to -V, and then again it is A B C D transpose is equal to -A minus B minus C minus D, and this is A B A C B D is equal to -A minus B minus C minus D, and this will give me what? A is equal to 0 because A is equal to -A, so A is equal to 0. D is also 0 because D is equal to -D, but I have C is equal to -B, and similarly B is equal to -C will conclude the same thing. So my E lambda is equal to -1. This it is span of this matrix 0 1 -1 0. That's how I wrote it, right? Yeah. Okay. And if you want, you can check that this matrix 0 1 0 0, or since I'm writing it like this, and this we have to check that this beta is orthonormal. I mean, this we can arrive at orthogonal. Let us first work with, because once we have orthogonal, just dividing by norm will give me orthonormal basis. And since check that beta is orthogonal or not, or we can just do Gram-Smith on beta will give us an orthonormal basis of V. Okay, and once we have that, we can conclude. But first thing is that whether this beta actually serves as orthonormal basis or not. Okay, so first thing to check is, I mean, if you do orthogonalization, note that these 4 matrices, you can just check this, okay, that this beta is orthogonal set. Okay, so note that this, if we take trace of B transpose A and so on for these matrices, everything falls. And but norm of, if I call this E1, E2, E3, E4, or let me call this beta 1, beta 2, beta 3, beta 4. Please check this. Please check this. Needs to be checked. Okay. Then norm of beta 1 is equal to 1 because it is trace of beta 1 transpose beta. It is trace of 1001 into 1001, and it is just 1. Or if you don't know, trace of beta transpose beta or A transpose A for any given matrix is always square addition of square of entries. Okay, so norm of beta 2 is trace of entries of beta 2 square. So it is, let me just write beta 2 transpose beta. Just then it is trace of this norm square. Just 0 square plus 1 square plus 1 square plus 0 square, which is 2. So therefore, if I take the norm of beta 2 is square root of 2, norm of beta 3 will be 1 and norm of beta 4 similarly will give me root 2. Okay. And then this new, if I call this gamma containing gamma 1 is equal to beta 1, gamma 2 is equal to 1 by root 2 beta 2, gamma 3 is equal to beta 3, and gamma 4 is equal to 1 by root 2 beta 4 forms orthonormal basis of T. Okay. Please take that this, even if you go from orthogonal normalization process, this remains as it is. V1 gives me same V1, V2 gives me same V2, and so on. Because trace of B transpose B for these four vectors becomes 0. These are orthogonal. You can follow Gram-Smith and you will end up getting the same set. Then just dividing by the norm will give me orthonormal basis. Is it okay? So if you have real linear transformation, and if we have real vector spaces giving linear transformations, or the linear transformations are on real, then we have to actually find whether the orthonormal basis is possible or not for given linear transformation. Okay, because we can't conclude that from the spectral theorem for normal operators, even if the linear transformation is normal. Because spectral theorem holds only for complex vector spaces, complex inner product spaces, and T normal. Is it okay? Please check that this actually forms orthonormal or this form orthogonal set. I will add that immediately to this, that Gram-Smith process and everything. But it will be great if you do that on my own. I would have done that, but since we are out of time, it will take time since there are 4 vectors and we have to do everything for 4 vectors to follow Gram-Smith method and so on. So is it okay for now? This is true. I will add the calculation for Gram-Smith to this PDF. And apart from that, any doubts here?
It is okay, madam. Clear.
Okay, so I will add the Gram-Smith process to this PDF itself, so that it will be clearer for you and you can follow it. But this statement is true. For this linear transformation, it holds. Okay, that orthonormal basis exists for given linear transformation. And apart from that, any doubts? Any doubts in the calculation I did and so on? Or any doubts in the today's session where it was not clear? Please let me know. Otherwise, we can close.
No doubt, ma'am. Thank you.
Okay, sure. So, okay, so I will add the calculation for Gram-Smith to this PDF. Other than that, yeah. And also, the question which was asked by Karthikeyan sir, I have added that to the miscellaneous PDF. Please check, and if you have any doubt, please raise it in the discussion. Okay. All the best for the exams, those who will be appearing for the exam. Yeah. Thank you.
Thank you,
Okay.
ma'am.